Yes. So we were seeing about the delta TLM, which is log mean temperature difference. In case of the parallel flow, delta T1 is TH in minus TC in, and delta T2 is TH out minus TC out. And the log mean temperature difference was coming this. This is delta T1 minus delta T2 divided by log of delta T1 divided by delta T2, which is the same. Okay. But then in case of counterflow heat exchangers, the log mean of temperature difference would remain the same. The delta T mean, log mean would be the same. Log mean would be delta T1 minus delta T2 divided by log of delta T1 divided by delta T2. But the definition of delta T1 and delta T2 is, in case of delta T1, it is T hot in minus T cold out. In case of here, it is T delta T2 is TH out minus TC in. What is the main reference? Hot fluid is the reference. In both the cases, hot fluid is the reference in calculating the delta T's. I hope it's clear. So this is equation 14 itself. 14 repeat. Equation 14 being repeated. Same thing. Now, if delta T1 is equal to delta T2, if it is the same, then what? If delta T1 is equal to delta T2, then what? What's the log mean temperature difference? Huh? 0 by 0 form comes. Then what? Log 1. Log 1 is 0. If delta T1 is equal to delta T2 here, then what? This cannot happen in cross flow or in parallel flow. It can happen in counter flow. What it will be? If then delta T1 is equal to, or delta, then log mean temperature is delta T, log mean is equal to delta T1, which is equal to delta T2. That's it. That would be the same difference. Same temperature difference, is it not? So log mean temperature difference, why do we use? We use so that there is no problem with, uh, we cannot calculate the delta T, is it not? So it is mainly to calculate the heat transfer. Observe, delta TLM is to calculate the heat transfer. Now delta T is the same and heat transfer is the same. What is the requirement of calculating the log mean temperature difference? So write this now. This may be very, very important, and in the interview these things are confused like anything. Or maybe in gate also it will come, where they will give such that delta T1 and delta T2 is the same. Oh, 0 by 0. Exam ಅಲ್ಲಿ pressure ಅಲ್ಲಿ ಏನಂತ ಗೊತ್ತಾಗುದಿಲ್ಲ. And in gate they give like that. Shatter. ಅದು shatter ಆಗಿ ಮತ್ತೆದೆಲ್ಲ influence ಆಗುತ್ತೆ. You do something wrong at one place which you think is easy, it percolates to other problems also. That pressure is distributed equally in all directions. Pascal's law. Correct? Domino effect. No, it's pressure. Domino we don't want. We want Pascal's law, where pressure in one particular because of the mistake, the pressure generated because of the mistake in one question propagates to other questions in both directions, in all directions. Okay, chalo. Next. So this is very important. So these kind of ವಿತ್ತಂಡವಾದ ನೋಡ್ಬೇಕು ನಾವು ಏನಿರ್ತದೆ ಅಂತ ಹೇಳಿ. So now another point, counter flow heat exchangers. Oh, cross flow is over. Counter flow is over. Now cross. Cross flow heat exchangers. Today I'll try to complete heat exchangers. Okay. So cross flow, what happens? You have one flow here, okay, and then there is another flow here which is happening. So say these are pipes. Oh shit, wait a minute. Let me put it properly. So we will have, say, some pipes here. Write it neatly. These are pipes, okay, and say there are baffles here. Right. And the flow is happening here. And then here there is a flow. Right. This is one of the examples of cross flow heat exchangers, is it not? So if you consider this cross flow heat exchanger, I'll say this is TH in and this is TH out. Okay, and then here we have TC in and this is TC out. Temperature out. Fine, cold fluid out. Okay. So now, one of the main problem what happens here is, see, if you consider the cross flow, the temperature difference here, if you consider temperature versus the length here, this is length, temperature profile here, okay, which is going, is all straight. This is the temperature profile, as it were. This is TC. So this is TC in, right? What comes out over here, for example, what is coming out, the temperature profile will be the one which is over here will have a lower temperature. See here, this will have a lower temperature. The next one will have a bigger temperature. Correct. Cross flow, that is the way. The TC in, what is going in, is having a lower temperature. See, will have a lower temperature, uniform. Right. Will have a uniform lower temperature, right? And when it comes out here, it will have the one which is near will have a high temperature, and the one which is going down away will have the bigger temperature, lower temperature, right? Makes sense. This is the temperature on this side. Makes sense. So this understanding has to be there. This is temperature. This is temperature. Makes sense. So understand that. So how to make the thing? Okay, so we have, see if you consider pH, say at any point, if you consider pH mean changes. Okay, for example, so we have to take a mean of both the temperatures. Okay, so we have to take. Hmm? Yes, please. Yeah, this is tea hot in. I'm very sorry. Tea hot in. When I rubbed it off, I wrote it wrong. pH. Temperature. These are the temperature distribution. The fluid which is coming from this side, the hot fluid, will have a low temperature. The one which is near here will have a high temperature. What is going in is with the same hot temperature. Yes, as it comes. Makes sense. Sujit, आता है क्या? Here cold temperature, it gets heated up. But then it gets heated up more where there is hot temperatures being there. Will heated up less where there are colder temperature in the hot. Yes. No, no. It is happening in this direction. It is 2D. This is here. This is going like this. This is going this way. The hot fluid is, if I put it like that, hot fluid is coming in this direction. Cold fluid is moving it. It's cross flow. Tubes are like this. Okay? Tubes are like this. These are the tubes over which the fluid goes. The cold fluid goes. Yes. See, this is the baffles here, which avoids mixing up here. It goes in one direction. Yes. Ah, exactly. It's a cross. Yeah, it's a cross flow. No? Cross flow. It's cross flow. It is not going along or counter. Then there are sometimes efficiency is based on economy. What happened? That also is possible. It's similar if you don't create, if you don't take into effect natural convection. If you take natural convection, then what should happen? If it is cooling by natural convection, not by forced convection, then what should happen? Hot fluid, hot should go like this, okay, and cold should go from bottom to top, or it happens. So don't have to worry. Natural convection, it makes it to happen. Exactly. True. The other way around. You're saying like that. Okay. So if that is the case, then we can good the engineering things. Actually, what happens? You have another pipes below, another line of pipes below. Okay, I got his point. He's thinking engineering. Okay. Correct. You are right. I appreciate your. He's saying, sir, why are you using like this, sir? Can't you use from top to bottom? Very nice. Correct. We could have used, but then there it is a cross flow, no doubt. Okay. But the effect of cross flow is not seen. The effect of cross flow is here also there are other pipes. Keep in mind. There are other pipes below. Okay. Anyhow you can do, is it not? Okay. So that particular way to use, we are using it. Okay. Even if it is one also, there is a difference. Okay. Whether it's like this way, there is a difference. Okay. So this engineering thinking you have to apply. Okay. So let us see here. Okay. So what happens here if I say there is a hot fluid which is going in. So what happens is if I say this is the hot fluid. Okay. So let us say this is TH in. Wait, this is cold fluid direction. This now gives a very nice 2D image. This to be understood. I'll write it in the next slide. Have you written this one? Finish writing this? Done? Okay. Done, mister? No. This one. Then I will make, okay, I'll put it in the next slide. So that the big screen creates a big effect. Imagine this, students. Imagine. Very important to imagine. It will change, is it not? Where is it more? More is where the hot fluids is coming in, is it not? Where the hot fluid is coming in, the temperature is higher. Yes, of course. It is at the end. This is what is coming out. Yes, exactly. Yes, no. At the end, the temperature is more. Over here, the temperature is more. Here, the temperature is less. Cold fluid is going in, cold fluid is coming out. When it is coming out, where the temperature is more? Here. Where the temperature is less? Over here. This is straight to this. This and this are straight. Okay. My drawing problem. Let me put it like this. Let me draw it neatly so that this and this are straight. Now I think it's clear. Correct. No? This is the temperature. My drawing problem. Okay. So done. Next. Done, Mister Rajji. Avita. ಆಗ್ಲಿಲ್ವಾ temperature distribution ನೋಡಿ the fluid which is coming in here is getting heated up the most, is it not? Because it is exposed to hot fluid. And when this hot fluids comes over here, its temperature reduces. So the cold fluid which is coming in is exposed to less hot fluid. The cold fluid which is going in like this is exposed to less hot fluid. So the temperature rise is lesser. If you consider hot fluid from here, which is coming here, it is this pipe is exposed to very cold fluid. So that obviously the distribution, the temperature distribution will be slow. Yes, slope like this. It need not be linear only. It can be anywhere out. Okay. Don't take it's exponential only. We cannot, we don't know. Okay. It depends on a lot of factors. Okay. It also affects on the conductivity of that material because the fluids. In fluids, conductivity is a function of temperature. So things are a bit different. Okay. Even here. Also pressures. Okay. Also some of the additives which can come. A lot of things are there. Okay. Done. Okay, next. So this is very important. Giving this time is important to understand. Okay. So let us put it in a better fashion, a big way. So let us say a cold fluid, the hot fluid is going, uh, yeah, sorry, cold fluid is going here. These are the parallel lines which are there, or tubes which are there here like this. Let us say this is the slot through which the cold fluid goes in. Okay, or here, let us say this is the cold fluid. Okay, so let us say this is the cold fluid, other way around. So in these pipes, cold fluid is going in. Okay, so this is cold fluid that is going in. This is cold fluid in. Okay, and over here I will say it is hot fluid in. And here hot fluid out. Sorry, let us put it like this. Okay, so let us have, okay, hot fluid in, hot fluid in, and this is hot fluid out. Let us say this is going in m dot h, and this is coming in m dot c. Okay, so m dot c is the cold fluid, the mass flow. What would be the temperature of the cold fluid? Here the temperature would be, say here the temperature would be Tc1, and here it would be Tc2. Okay, Tc2. Okay, and this Tc2 will be higher than the Tc1. Tc2 will be higher than Tc1, and later on it will increase. It will increase. It will increase. It will increase. Right? So write it a bit more higher. Right? It will increase. Now there will be something at somewhere we have the mean temperature. So I'll say this is Tc mean. This one is Tc2 mean temperature, where Tc2 is mean temperature of exiting cold fluid. Exiting cold fluid. Similar way, if you consider the hot fluid, yes, correct, correct. I'm very sorry. It will be opposite. Very sorry. And this is because of Nag has used the other way around. I used it this way and thought this is also same, is it not? So this is correct. Very good, Bharat. So I'll say this is TC2 mean, correct? And this is as a TC2 dash, and I'll say this is TC2 double dash. We can have that, or we will have this double dash here and single dash over here. It varies in the end. Okay. Similarly, if you consider the hot fluid, if you see here, you see the temperature distribution. Here the hot fluid will cool, and here the hot fluid will cool, but not as much as. But keep in mind, we have to see that Tc double dash is greater always than Th2 double dash. So this is Th2 double dash, and this would be Th2 dash always, and this is the mean temperature. This is Th2 mean, and here Th2 mean temperature of exiting hot fluid. Very important. Exiting hot fluid. And exiting hot fluid. Exiting hot fluid. Now, here, whatever the mean temperature is there on this side, here we have to keep in mind that TH2 dash is always greater than TC2 dash, and TH2 double dash is greater than TC2 double dash. Is it not? Am I correct in saying that? Correct, no. Can I say that? Say so. Wait a minute. Wait a minute. Can I say so? Or I cannot say. TH2. Can I say that? No, I cannot say it. I cannot say that. Not always applicable. Is it always applicable? Let us see. See here. TH2 is over here. It's cooling. It can cool much more. It can cool much more than TC2, which is getting heated up. So TH2 can be any way, is it not? It can be both ways. And and TC2 dash can be greater than TH2 dash. Is it not? TC2 dash can be greater than TH2 dash. Yes or no? TH2 dash can be greater than, or can be TC2 dash can be greater than TH2 dash. Is it not? It may be cooling down more. Possible? So both are possible. Is it possible? Yes, it is possible. See, let us say here, let us understand. Here it is, say, 30 degrees centigrade. No, wait. We are not worried about what is atmospheric and all those things. We are worried about, can this happen in general? Okay. See, let us say atmospheric air only, which is coming at 30 degrees centigrade. But still it attains the same temperature. Wait. Let us see. That's why I put the numbers. Then numbers, when you put, you can understand. Okay. So when it is coming out here, okay, TC2 and TH2. Okay. So here hot fluid, say it is coming at 300 degrees centigrade. 300 degrees centigrade. And it is coming out at, say, 40 degrees centigrade. Can happen. Correct? Okay. Now 30 degrees centigrade, what is going out, can go out at, say, 45 degrees centigrade. It can also go out at 35 degrees centigrade. Both are possible. So what is this first case? First case is TH2 dash is greater. TH2 dash is greater. The second case, okay? Yeah, 45. This is 40, and this can be anything else. Okay, this is 40 degrees centigrade. You can see. Okay, so if TC2 dash is greater than TH2 dash, then it is the case of this. If it goes out with 45 degrees centigrade, it is this case. Both are possible. Yes or no? You have to think now, students. Okay, you have to think now. In the exam, you don't have time to think. You'll just buckle under the pressure in the direction of the lowest moment of inertia. Let's see buckling later. Chalo. Clear, no? Similarly, here, what is 300 degrees centigrade here, what's coming in, can come out as, say, 70 degrees centigrade. And what is going out here, TC2, can go out as say 150 degrees centigrade, or it can go out as say 60 degrees centigrade. Can happen. It's getting heated up. Both possibilities are there. So that has to be understood. Okay. Sure. Write this down. Write this down. Write this down. And PH2 double dash. Now let us see if now here we have to see the log mean temperature difference, right? Let us see. Ahorita. ಆಯ್ತಾ ಮಕ್ಕಳೇ? ಈಗ next. ಈಗ so what happens is here delta T1 is given as TH1 TH in minus TH in minus TC in, and delta T2 is given as TH mean, or yeah, TH, here we have written TH1, is it not? Okay, we will write TH1 minus TC1, and this is TH2 mean minus TC2 mean. Okay. And we will write delta T log mean. Delta T log mean is actually equal to same equation, delta T1 minus delta T2 divided by log of delta T1 divided by delta T2. Only thing is that to calculate the other things we have to take mean. What is the equation, students? See the equation number 16, 17, 15, 16, 17, 18. This is 17 and 18. This is 14 repetition. Right. So same thing is applicable here. Now, second case which can happen is condensation. If there is a fluid which is condensing, or a fluid which is say evaporating, both the cases, the chances of counter flow, heat counter flow, or parallel flow, all those things doesn't hold good there, or cross flow is getting evaporated. What do you call cross flow or counter flow? One temperature is the same. Is it not? So this comes as a separate case where we have condensing or evaporating or heat transfer with phase change. Write it this down, finish and tell me. I'll wait for Bharat. Once Bharat says done, I'll go further. Because he spends time in understanding, is it not? He does not write without understanding. He's like Ganpati. You know Ganpati? When Vedavyasa wanted to write Mahabharata, what did he do? He said understand and write. Because his writing speed was very high at first. So when he understands and writes, it takes time. So like so, so done. Next. Now heat transfer with the phase change. Heat transfer with the phase change. So if you consider heat transfer with the phase change, see if you consider if it is a evaporation that is happening, if one fluid is evaporating, then evaporating fluid has to be the cold fluid. The hot fluid is causing it to evaporate, right? So cold fluid evaporate. So this is the temperature. This you say A naught, or that is length. We will say length of the heat exchange. Okay. What's going to happen here? The cold fluid will be T saturation. I'll write in another color so that impression is created. Okay. So this is the cold fluid. Tc is equal to T saturation. It is at the same temperature. What about the hot fluid? Hot fluid can go here. So whichever direction it is, we are not worried about. Okay. So T saturation, whether it's going this direction, that direction does not matter at all. Okay. So here, what is happening? T hot fluid, it is going in this direction. This is the T hot. So this is TH in, and this is TH out. Right? And TC will be the same. Right? This is evaporating. This is the case of evaporation. Evaporating. Write it along with me, students. Cold fluid. Correct? This would be same, is it not? Or it may be the other way around also. It may go in the other direction also. So, so it may be something like this also. We start from here and we go down like this also. It may be the other way around also. Okay? Both cases can be there, right? And this would remain the same. Okay? And this would remain the same. Correct? And this is called, this would be T TH2 only, Tc is equal to T saturation. Consider here also Tc out or in, we are not worried. Saturated temperature. Same thing can come with when it's condensing. Same thing can happen when the hot fluid is condensing. See, hot fluid condenses. Okay. So it may so happen that hot fluid condenses and cold fluid will increase in temperature. So hot fluid is at the same temperature. So TH is equal to T saturation. Condensation. It's condensing. Whereas the cold fluid, its temperature is rising. Right. So cold fluid temperature rises. Right. This is TC1 and this is TC2. So it may be in this direction or it may be in other directions. Maybe in other directions. Both directions. Fine. This is the T axis. This is the temperature axis. Here, hot fluid condensing. Correct. Both cases. ಇಲ್ಲಿ ಕೂಡ ವಿತರಣವಾದ ಇದೆ ನೋಡು. Let us see some ವಿತರಣವಾdas. Done. Right, it neatly don't. Done. Don't. No urgency. Tell me when you're done. Online students, I hope you're clear.
Yes, sir. ಆಯ್ತಾ? Sorry, next one. And the side over here is this. Okay. See now, what is delta T log mean for condensing fluid, or you can say, or evaporating fluid, evaporating gas. For evaporating case, what is delta T log mean? That would be delta T1 minus delta T2 divided by log of delta T1 divided by delta T2. Is it not? Correct. Now this can be equal to delta T1 is what? TH1 minus TC, which is at a constant temperature, minus TH2 minus TC, which is also at constant temperature. Divide, write it along with me, students. It's easy. Just substitution. TH1 minus TC divided by TH2 minus TC. Okay, which will be equal to, if you consider, okay, if you consider this would be equal to, okay, this would be equal to TH1 minus TH2, TH1 minus TH2 divided by log of TH1 minus TC divided by TH2 minus TC. One second. This was the delta T.
log mean. Similarly, wait a minute. Similarly, if you consider the other way around also, one second, I'll go to the next line. Okay, similarly, or condensing case, delta T Lm would be equal to. Observe here, TH1, what cancels TH1, that is TH minus TC1, right? Minus TH minus TC2 divided by log of TH minus TC divided by TH minus TC2, TC1 here, that's it. Okay. This would be equal to, so TC1, TH and TH cancels. What do you get? You get TC2 minus TC1 divided by log of TH minus TC1 divided by TH minus TC2. Makes sense? Yes. Now I'll go back. This you can substitute and do others. Tell me what is the question. Missed the question? Did not write. Okay. I should be careful. If it's a question, I should go there only because I should not forget the question. Because I do something else, then the previous question will be covered. This is what happens in classes, is it not? Live or online or anything. You have a doubt and you don't know whether to express that doubt or whether to hear what is being told. So when you start hearing what is being told, the doubt is evaporated. You don't know what you are supposed to ask. That's why class going slow is very important. Huh? There is no counter flow at all here. Where is counter flow? Where is parallel flow? The other way. That's it. It can be a negative. It should be negative. No. TH1 would be that. If it's other way around, entry will be here, is it not? No, 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 no. This is not TH2. Okay, this is TH out. Okay, I'll say TH out is TH1. Okay. I made a difference. So this is TH1. This is TH2. Write it TH2 because this is TH2. That will be TH1. This will be TH1. Getting that much. So there's no question of counter flow or counter flow or uh, parallel flow, is it not? Where it is entering, that is important, is it not? So here, this will be TC1. I have written it. Makes sense. Easy. Done. Next, we have seen. So let us go with problems. Then we will go to NTU. Okay. NTU stands for Nanyang Technological University. Now, when I say something, to give you some perspective, which is good colleges, which is bad colleges, have a good, nice book. Okay? And somebody has got it, you will take good advantage. My book is with our Divya Raj. Correct, Divya? This book I'm telling. So we'll take advantage of everybody's books. Whose is this? Sharon? Then Bharat. Heat transfer. Heat exchange, does it not? So let us see what are the questions which has come in heat exchanges. Simple question. என்னடா சிம்பிளா? Effectiveness we will see later. So we have questions on effectiveness as well as, so here this has come in 2000 millennium question, 2 marks. So we will see the millennium question. Okay, the question is like this: air enters a counterflow heat exchanger. Air enters a counterflow heat exchanger at 70 degrees centigrade and leaves at 40 degrees leaves at 40 degrees centigrade. Water enters water enters at 30 degrees centigrade and leaves at 50 degrees. The LMTD in degree centigrade is A 5.65, B 14.43, C 19.52, and D 20.17. So what is it? So in counterflow, delta T1 is equal to solution. What is delta T1? Delta T1 is, you can, if you forget it, you can write this. Okay, this is T hot becoming cold, and this is T cold becoming hot, right? So this is TH1, this is TH2, this is TC1, this is TC2. Delta T1 is this, right? Delta T1, this is delta T2, right? So delta T1, this is equal to H1 is 70 and this is 40, and TC1 is 30 and this is, so delta T1 is equal to TH1 minus TC2, which is equal to 70 minus 50, which is equal to 20, and delta T2 is equal to TH2 minus TC1, which is equal to 40 minus, which is equal to delta T log mean is equal to, delta T log mean is T1 delta T1 minus delta T2 divided by log of delta T1 by delta T. Okay, so that will come as log of delta T1 minus delta T2. Now the question is, should we convert it into Kelvin? Is the question. Answer is no. Okay, it will come even in degree centigrade. But thing is that uh, delta T always isn't, whether it's in Kelvin or degree centigrade, it is the same. So what will happen here? You have 20 matters. Okay, but here it does not matter because here also delta T1 is it, here also delta T2 is it. Correct. So log of 20 by 10. Right. So what is that? Log of 1 by 2. Right. What's the answer you got? 14 point. So easy answer. Yeah. इतना easy सटा सट हुआ. Next question. This is one good question. Shall we go further? Done writing everyone? Next question is like this. Okay. Very good question this is. This has come in 2002 for 1 mark. 2002 for 1 mark. for the same, write it along with me, students. For the same inlet and exit temperatures, inlet and exit temperatures, inlet and exit temperatures of hot and cold fluids, hot and cold fluids. The log mean temperature difference, the log mean temperature difference, difference. LMTD is a greater for parallel flow heat exchanger heat exchanger than counter flow heat exchanger. B greater for counter flow heat exchanger than parallel flow. C same for both parallel and counter. And then D depends on properties of fluid. And so forth. So its answer equal according to equal. No, let us understand same inlet and exit temperature of the hot and cold fluids. That means the inlet temperature of the hot fluid for the inlet temperature of the hot fluid and exit temperature of the cold fluid, it's both same. Okay, same temperature of the same inlet and exit temperature of both hot and cold fluid, both are same. Okay, so what is happening here? If I say a counter flow, first of all, let us write a parallel flow heat exchanger. Yeah. Okay. So hot fluid. So we have TH1, TH2, and you have TC2, TC1. This is parallel. Counter flow, you have to write in such a way that TH1 is the same TH1 and TH2 is the same TH2. Fine, right? TH2. TC1 is same TC. This is what I think. Same inlet and exit temperatures of hot and cold fluids before. This is what I assume. Yeah, both hot and fluid. See, inlet temperature should be same. TC2 will be here. I think this is what is the understanding. Yes or no? Is there any other thing which we can do? It means correct, no? Okay, now tell me. Understand. Where the log mean temperature difference will be higher. Parallel will have higher log mean temperature difference. Think. I'll see the answer by the way. Yeah, that's correct. No, no, I'm not saying that. I'm not saying that. Counter flow will be higher. Yes. Okay, let us understand with some more things. Okay, so here, can we prove it? Is the question. Okay. So have they proven it? No. Not even given that. The explanation they have not given. Let us understand how, why counterflow heat exchanger has more temperature difference. What is the reason? Huh? See, TH1 is delta T1 is bigger, delta T2 is smaller, no doubt. So we have LMTD if you say delta T1. But what about the log? So what happens? Delta T1 is bigger, delta T2 is smaller. So you have a big number divided by big number, log of a big number. Here the difference between big and the small number. Now here, this is parallel flow. Now if you take counter flow, this is parallel flow. I'll write like this parallel. This is parallel flow, I'll say. Okay. And then LMTD for counter flow, okay, for counter flow, I'll say delta T1 minus delta T2 divided by log of delta T1 by delta T1 for the same one. Now, delta T1 will be delta T1 for counter flow TH1 and TH2, right? Now, how do you come arrive at it? Wait, huh? Can you arrive at it from the this one? I know it intuitively, that is how the case is, but we have to arrive at things, is it not? Mathematically, we can take an example and we can see that's a different case. But if we could mathematically prove it, that would be much better, is it not? Huh? We can substitute some numbers and see that you can do it now itself. That is not the case. So if you're good in math, huh? Hmm. Which one? Tell me the substitution. What you said? TH1. What do you take? What was your substitutions? Ah. So let us take one. TC1. Huh? 70, 40, and 30 and 50. Do that. But here this cannot happen. TH2 cannot be greater than TC2, less than TC2. In case of parallel flow, this is not possible. So this has to be 40, this should be 38. Huh? Okay, let us take it. Now put it and see. Correct. No, this is okay. This is okay. Now tell. Now put it into the equation and see. But let us make an attempt to substitute, do it mathematically. I think we should open it up in terms of TH1, TH2, delta T we have to change. And if we divide by, we have to non-dimensionalize it. Then I think this can be proved. But it's okay. It's a general case that counter flow will be higher for the same. Generally, counter flow is higher. So this you can take it as a theory. Okay, you cannot have TC2 greater than TH2. Water flow is here. So fine. Chalo, next. Next question. This you have to take it as a rule. Okay, take it as a rule. Okay. Next question. Okay, this question has come in 2003 for 2 marks. This question has come in 2003 for 2 marks. Okay. In a counter flow heat exchanger, in a counter flow heat exchanger, the hot fluid for the hot fluid for the hot fluid, the heat capacity equals 2 kilojoules per kg Kelvin. Mass flow rate equals 5 kg per second. Inlet temperature equals 150 degrees centigrade. Outlet temperature equals 100 degrees centigrade. For the cold fluid, heat capacity equals 4 kilojoules per kg Kelvin. And mass flow rate equals 10 kg per second. Inlet temperature inlet temperature inlet temperature equals 20 degrees centigrade. Neglecting heat transfer to the surroundings. Heat transfer to the surroundings. The outlet temperature, the outlet temperature, outlet temperature of the cold fluid is fluid in degree centigrade is A 7.5, B 32.5, C 45.5, and D 70. Which one? B. Let us see. If you say B, we let us see. And you are right. It's B. Easy. What did you do? MCP delta T. That's it. Nothing great. No LMTD, nothing. Counter flow, cross flow also, we need not. MCP delta T. That's it. MCP delta T for the solution is like this. Solution is MCP M dot CP delta T equals M dot Cp for hot fluid is equal to M dot Cp delta T for the cold. What is that? This is M dot is for the hot fluid is given as 2, Cp is given as 5, delta T is given as 150 minus 100. This is equal to M dot in the second case is 4, Cp is 10, delta T is Tc in is 20, right? Delta T is what is T exit minus T in, which is 20. Correct. The only thing is that you have to find. So this same thing is it not 2 into 5? No, it's 4 into 10. Is it not? So it's different. Okay. So you get 150 minus 150, 100, 500, right? Divided by 40 plus 20 is TE. What happened? Cancel ಆಗ್ತದ ತಪ್ಪಾಯ್ತಾ ಕಿಲೋ ಅದು ಬೇಕಾಗಿದೆ ಈ ಥರದ್ದು ಬೇಗ ಬೇಗ ಮಾಡುವಂಥ ಇದು ಬೇಕು ಆಯ್ತಾ ಆದರೆ ಹಾಗೆ ಮಾಡೋ ತಪ್ಪು ಮಾಡಬಾರ್ದು ಪ್ರಾಕ್ಟೀಸ್ ಬೇಕಾಗ್ತದೆ ಸೊ 500 by 40 ಎಷ್ಟು ಬಂತು 500 by 40 400 400 ಆದಮೇಲೆ ಯಾ ಸೊ ಇಟ್ ಈಸ್ 10 12.5 plus 20 that is equal to 32.5 calculator ಬೇಡ ಅದಕ್ಕೆ ಅಲ್ವಾ this can be IES type of question which does not require any calculator. Okay, next question. Then I tell you. Okay, next question. This has come in 2004, 2 marks. That time it was 2003. Did I write it? Yes. 2004, 2 marks. The question is like this: in a condenser, water enters at 30 degrees centigrade and flows at a rate of 1500 kg per hour. The condensing stream the condensing stream is at a temperature of 120 degrees and cooling water leaves the condenser at 80 degrees. Specific heat of water is 4.187 kilojoules per kg Kelvin. Joules per kg Kelvin. The overall heat transfer coefficient. The overall heat transfer coefficient is 2000 watt per meter square Kelvin. The heat transfer area is the heat transfer area is A 0.707 meter square, B 7.07 meter square, C 70.7 meter square, and D 141.4 meter square. What's the answer? Almost every question paper this has appeared, students. Okay, one question on heat exchanger design has appeared. 2002 it has appeared in both the this one, papers. 2021 set, 2021 one set. Yeah, all the other things one set. One question on heat exchanger design. In 2014 set 2, there were 3 marks question on heat exchangers. One question, can steam condense at 120 degrees centigrade? At what temperature does steam condense? 100 degrees centigrade, right? Why is it condensing at 120 degrees centigrade? It may be. It might be. Additives. No, though there is no additives. I know that the person who is doing that, there was no additives there. Very sure about it. So just tell me what is the reason. Kirtan. Pressure is less or high? Why high? Or low? You have to take whenever the pressure is high or low, we know. So at atmospheric pressure, it condenses at 100 degrees centigrade. But if it's higher temperature, then it condenses at higher temperature. If the pressure is high, it condenses at higher temperature. Why? Because if you take case of pressure cooker, water, see whenever you relate something, then only will happen. Or you say on the Mount Everest, the water boils at 69 degrees centigrade. Got the point? That's how you take it. Cooling water leaves at 80 degrees centigrade means what? Is it the condensed steam which leaves at 80 degrees centigrade? No, the cooling water, which is at 30 degrees centigrade, leaves at 80 degrees. So what you should calculate? You should calculate LMTD here, is it not? So what is, how do you have to do here? It is solution. See here, delta Q is equal to, Q is equal to, Q is equal to MCP delta T, which is equal to U naught U A into delta T log mean. Correct? Like this you have to find it. So delta T is for this one. M is flows at 1500 kg per hour. CP is 4.187. Delta T is 80 minus 30. and U is given as 2000. Area we do not know. Delta T log me we can calculate, which is TC2 minus TC1 divided by log of T hot minus TC1 divided by T hot minus TC2. T hot is the same, is it not? So you get this like this. So you can calculate this. This is equal to 2000 into area into TC2 is 80 minus 30 divided by log of 120 minus 30 divided by 120 minus 8. One step answer. So you get area as how much? 0.707 meter square. Okay, let us see. 5.7. Yes, right answer. One answer. Correct. Chalo, we'll stop it here, students. We'll meet at 4 o'clock